A very good afternoon, dear faculty members. I hope my voice is audible to everyone. Can inform your friends and colleagues to join the session as soon as possible. We have just 100 participate in Zoom. So I request, please inform your colleagues or friends to join the session. Rupal sir, good afternoon.
Yes, good afternoon, ma'am.
Yeah,
And good afternoon to all of you.
you can start the session, sir.
Okay. Yeah, so yesterday we have studied everything about quantum gates, and now we are starting. Let me share the PPT. Hmm, Yes. So, so yeah, yeah, we have covered uh, double C NOT gates. So the purpose of all these gates was to establish the quantum logics here, right? So every gate is having a certain logics. So this is a double control gate, and now we will talk about quantum circuits. So for the quantum circuits, I was not having some slides, so I will use the whiteboard of this Zoom platform for the quantum circuit explanation. So yes. One minute, it's loading here. Yeah. So so ultimately, we are now till now we are having the X, Y, Z. These are the single qubit gates, H gates, and secondly, we are having a C naught gate, that is a double qubit gate, and CC naught gate. This is this is gate is also called Toffoli gate on the name of that one. With these combinations, we have to use make a quantum circuit. All these combinations of the gates will give us a quantum circuit. So as usual, as the electrical circuits and all, we are having two arrangements. So as in the quantum circuit, the sequence of the gates can be in the two arrangements. The first arrangement is series arrangement, and the another arrangement is parallel arrangement. Parallel arrangement. So in the series arrangement, what mathematical operation we have to perform, that we have to see. And in the parallel arrangement, what are the mathematical operations are performed that we have to see. And when we are seeing these arrangements, then we can say in a line that the series arrangement is followed by a scalar multiplication. This scalar multiplication and the parallel arrangements, all the parallel arrangements, wherever we find it, they are followed by the tensor multiplication. They are followed by the tensor multiplication. And this tensor multiplication is because all the things are parallel. So this tensor multiplication is in two way. One in the inputs, because we are providing the inputs, and second one on the gates, because gates are in parallel. So the parallel arrangement is followed by tensor product, and that two tensor product is operated simultaneously in the input side also as well as in the gate side also. And when we are calculating this input side, then it will convert into the series operation. That means we can do a simple scalar multiplication between this output and between this output. This output of tensor product, this output of tensor product. So the output 1 and output 2, we can do a scalar multiplication. So while explaining the gate, what happens, most of the faculties are doing like this. They are explaining series and parallel combination. But I think we have to follow this thing that in the series and parallel, you can classify in a primary line itself. Now, so for example, suppose in the series, suppose we are taking, suppose there is X gate, then in a series arrangement, suppose we are taking a Z gate like this, and then suppose we are, for example, this is example one. So suppose we are taking the two gates as a series, then this is the input, this is the output, right? So in the input state to the output, the pipeline will be like this. Hello, hello.
Yes, sir, you're audible, sir.
Okay. Yes. So 1 minute. Somebody has taken the control for this. Okay, now I got it. Yeah. So yes. Um, 1 minute. Susmita ma'am, there is something. Somebody else is taking the control on the whiteboard.
Sir, nobody.
So I'm having this notification that something Krishna Pal like that is taking control for that.
Okay, no, actually it is locked, sir. No one can have, like, they can't do anything.
Okay, because I'm I'm zooming this
Okay.
one, and suddenly I'm getting the notification somebody else is.
No issues, sir. If you have
Oh,
some like any issues, you can just drop and you can rejoin.
yeah, that I know with the sharing option.
Yes.
Yeah. So yeah, we were arrangement. So suppose in the series arrangement we are having this circuit. Then the first rule follow in the series as well as in parallel side, we have to do the calculation This Mohit is presenting something, and I was not having the control. One minute. Hmm. So yeah, I was saying that uh, we have to calculation. We have to take the calculation from the right to left. So there is a rule in the quantum circuits that all the calculation we have to take in from the right to left. Okay. So suppose in the series circuit we are doing like this. This is a series circuit. We have to calculate this circuit. And suppose input we are having either 0 and 1. Okay. So suppose look, 0 means cat 0, 1 means cat 1. Sorry, write it. Then the calculation we can do like this. From right to left, we have to do the calculations. So, mm, I'm putting this. One minute, one minute. Okay, I'm just sharing that PPT. On that PPT, I will use that pen. One minute. Hmm. So, yeah, we were talking about the series arrangement of X and Z gate. Suppose then in the output may be 0 or 1, right? So, but natural because we are having the X gate we are having the operation. The operation is from the matrix, unitary matrix. We are having X gate. So the X gate unitary matrix as a Pauli exclusion matrix 0, 1, 1, 0 for the X gate matrix for the like this. This is the matrices for the X and Z gates, right? So for the calculation side, we have to take from right to left. There is a fundamental rule at here that we have to take the calculations from right to left. So first we will take a Z, then the matrix of X, and we have to multiply this matrix from Z to X. And after that, after multiplication, the scalar multiplication. Okay, this time it is looking like that if we will do the multiplication. See, just note this line that the scalar multiplication of the matrix don't follow the commutative law. So it is not equal to either sequential, it is depends on the sequence. If you are taking right to left or left to right, right? So, so if normally a student is do like this, so it will be a wrong one. So we have to follow this right to left. So right to left means we have to take the matrix of Z first, that is 1, 0, 0, minus 1. Then we have to take the matrix of X then 0, 1, 1, 0, like this. Then we can do the multiplications for this row by column multiplication. We have to do like this, then this, and this is, oh, sorry, this is not the row by column. Yeah. So this is row, this is column. So row by column multiplication we can do this and write it like here. So we will get it again one matrix for that by how by multiplication. Then this matrix we will multiply on the inputs. Then the input is will be either 0 and 1. We will multiply this input. If the input is 0, we can multiply this matrix by 1, 0, or the input is 1, we can multiply the matrix by the 0, 1. Then we will get the final result of the matrix. Right. So that is a rule we are following. The rule we are following that right to left, we have to do the calculations first. And then the right to left calculation. And then in the series, there is a scalar multiplication only. So we don't have to do anything else. only we have to do a scalar multiplication in the matrices. Then we can get a final matrix. And we know that in quantum, this is very important thing. We know in quantum, this matrix, whatever matrix we are getting, this matrix is work as a gate. This matrix is working as a gate, right? So now coming to the series parallel connection. In the parallel connection, suppose we are having a same gate as a parallel, suppose X and in a parallel. So, but natural when we are going on the parallel, so we are following a two inputs. So that is the one input, another one is this input. Okay. So when we are following a two inputs, it means suppose we are following Q1 and Q2 like that. So two inputs. Then what we have to do, the simple rule, it will apply it here also. We have to do the calculation from right to left like this. So that when we are doing calculation from right to left. So for in the right side, we are having this gate. So in the parallel, we have to do the multiplication, tensor multiplication. So the tensor multiplication of x and z we have to do first. So and yeah, those one thing also need to be remember. Then when in the parallel, so in the parallel, there is also a question from either we have to do it top to bottom or bottom to top. So in this sequence, the right to left and top to bottom. So these two rules in the parallel we have to be remember that x and y, x and z. So first we have to take the x, then we have to take z. So z here is 0, like that. And then this tensor multiplication. So as we were saying that tensor multiplication is nothing but diversification of dimension. That means the same matrix we will multiply by 0 and we'll place it here. We'll place it here. The same matrix we will multiply by 1 and place it here. The same matrix we will multiply by this, place it here. Same matrix multiplied by this, place it here. Right. So here, so this is 4 into 4. It is 4 into 4. This matrix will automatically convert it into the 8 into 8 matrix. So that means dimensions are multiplied at here and dimensions are expansified. Right. So this is the tensor multiplication of matrix. So finally we are getting a one matrix. So this matrix will work as a gate. We don't know what gate it will follow, but yet it will work as a gate. Now the same thing we have to do in the inputs. So with the inputs, Q1 and Q2 are the two inputs. So we have to take the tensor product of the input, right? And we know that in the two states, because these are the two states, the basic states are 4, 0, 0, 0, 1, 1, 0, 1, 1. So any of these things can be presented the input. Okay. These are nothing. These are the tensor product of 0 and 0. So these are the direct tensor state, tensor product. So tensor product of 0 and 0 state, cat 0, that will give you a this state automatically. That I told you yesterday. So here you will get this basic states what you have made already from the tensor products like this. So 0, 0, 0, 1, 1, 0, 1, 1. Then you just apply that matrix at here, right? You will apply this matrix at here and just do the simple multiplication, scalar multiplication. You will get a one output matrix for that. That matrix may coincide with some of the gate or not. It depends on the inputs and the calculations. Now, suppose we are having three gates X, Y, and Z. Then again, the same rule will apply here. What we have to do? We have to, and this is the suppose Q1, Q2, Q3. So same rule will apply. Will here tensor product, and so we will do the tensor product first, top to bottom, top to bottom. Top to bottom means first the tensor product of X and Y we have to evaluate. We will get a matrix. We will get some matrix. Then we will evaluate the tensor product of this matrix, means this matrix with Z. Z is also a matrix, right? Then you will get a final matrix. Then in this final matrix, what we will do in the final matrix? Now this is the resultant of this. So in the final circuit, for our understanding, we can understand like this. This is the final one final gate, and the matrix of the gate is will be like this, right? So what we have to do here? Here also we have to do the cross product. Oh, sorry, tensor. Okay, tensor products. And when we will get a tensor products of three states, we are having the tensor products of the three states like that, either 000 or 001 or 010. These are the direct tensor products of the three states. Until unless the states are bounded by zero and ones, only that. Okay. So when we will get this when we will get this matrix, so any of the state can have Q1, Q2, Q3. So any of the state we can get it at here. And for every state 000, 001, 4010, we are following a matrix at here that this is a matrix for 000. This is a matrix for 001. This column matrix. This column matrix was for 000. So like that we will go in the sequence, and we will follow the until the last stage. So how much states will be there? 8 states will be there, and there are 8 matrices. So for the input side, we can say that we are very well sure that it will have a column matrix like that, either this or this, like this. We will have any of the one state in the input, and in the uh, this gate, final resultant gate, we have evaluated a final matrix here. Then we will go on the simple multiplication, but everything will go on the sequence from right to left. If we want to multiplication, then we have to do the multiplication. We have to write this matrix first, then this matrix first. Okay, this is the punch thing at here, that it's a very keep in mind that we have to do a first this and then this one, because the matrix multiplication is not commutative. So the matter that either we are taking right or we are taking left, that matters a lot. So like that we can do the parallel multiplications. Okay, so there are the series and parallel combinations of the circuits we can make it. Now the question will arise, the mere difficulties will come like this. If if the condition is like that, one gate is of 1 qubit. If we are having in the circuits, one gate is of 1 qubit, another gate is of 2 qubit, like C naught gate. Like this. So this is first gate, this is second gate. So here the confusion will come. Now what we have to do? Because here there is no touching of the second inputs for the first gate, this X gate. Okay. So what we can do here? So in these type of cases, for our sake of easiness, what we can do, there is a concept of no operation gate, NOP gate. When what is the no operation gate? So this is symbolized by this unit matrix I. Because here the main thing is that in the that matrix we can represent as a gate. So that means unitary matrix is also we can represent as gate. So any cross, either 2 into 2 or 3 into 3, whatever, or 4 into 4, whatever. And this is a matter that odd ordering we are taking in the matrix here. Why? It depends on 2 to the power 1, 2 to the power 2, 2 to the power 3, like this. Right. That's it. So, so any order of unitary gate, identity gate, we can take it. And this gate will do nothing for the inputs. That's why it is called a no operation gate. So, for the sake of clarity, no operation gate means whatever we want, 2 into 2, 4 into 4, 8 into 8, we can have this matrix. And the identity matrix means the diagonal element will be one only. Okay, so that is the identical matrix, unit matrix. So, mm, so what we can do here to resolve this problem, we can install a identity gate here. That is called a no operation gate. So so if we will have a no operation gate at here, then now this is a C naught gate, and this is the parallel arrangement of two gates X and I. Now we will get the matrix of that separate matrix. We will get a separate matrix of that, and then it will convert it into like this. This is a separate matrix for this gate. This is a separate matrix for C naught. So now these two are is in series. Now we can do the simple multiplication of this to this matrix. This is a new matrix. This is a new matrix. So we can do n1 to n1, n1 to n2 simple multiplication. So like that. So if suppose for the same example, if we are taking mm, so what we can do the parallel means tensor multiplication of X matrix with the I matrix. So the X matrix is like this: 0, 1, 1, 0. So the I matrix we can take it only 2 into 2 because X is 2 into 2. Only then we can do the things. So we can do like this: 1, 0, 1, 0. And then tensor multiplication we have to do. So for the tensor multiplication, the same thing will go here, same thing will go here, like this and this. We can write it at here. So we will have this matrix, then we will have the C naught matrix, 4 into 4. Then we can multiply that these matrices. But multiplication rule is right to left. So first take this matrix, then keep it this matrix and do the multiplication. Then you will get a final results. Okay. So the matrix multiplication, the main thing is that whenever we are doing the matrix multiplication, we are doing by row by column. So the order of the row and order of the column that has to be same. Only this thing we have to see at here. So these are the series combinations and parallel combination of the circuits, and some of the characteristics of the circuits that I also want to describe it here. That So, so there is no fan in, no fan out allowed. So there is one-to-one mapping in the quantum circuits always, right? So first thing is that in the circuit we have to avoid multiple input, same output like that. Okay. So that's why we are implying this I gate, no operation gate at here. Second characteristics is that when we are measuring, something, so the measurement sign we have to put like this. This is the measurement sign. This accounts for measurement. This is the measurement. And after the measurement, whenever the classical is there, we will follow the double line. Whenever the quantum is there, we will follow the single line. This is the usual notations the mathematicians and all the division and all that has made. That to differentiate the quantum and classical purely. So the thing is that after measurement, suppose the same gate, we can take it here. X, suppose Y, and there is a suppose C not gate. C not gate. There is a input Q1, input Q2. So we are having the outputs in the at here. Suppose these outputs are P1 and P2, like that. So if we want to measure the this P1, then we can fix it and mark the symbol like this. And after this symbol, this is very necessary. We have to make it double line to show that it is converted into the classical. As we were talking yesterday, that after measurement, all the quantum states are converted into the one state, that is collapsing nature. So that means when it is converted into the one state, then it means there will be a classical nature. So like that. So these are the characteristics of the quantum circuits, and any circuit we can observe, and depending upon the required conditions, so we can form these circuits in the later on. List in last half an hour, we will form these circuits in quantum coding in the cascade. So now we are moving towards the part of hmm, algorithm. So Deuce, we have introduced Deuce in a very first slides and the last day slide also. So now everybody knows that Deuce has introduced a very first algorithm in the quantum. So they have given the application of this algorithm is not so much, but only to prove that the quantum supremacy over the classical supremacy. So Deuce has worked on the problem. That problem can be solved with the quantum way or not. So what the problem was? The problem was with the Deuce that he has taken a function fx, and mathematicians from a mathematician point of view, this function can have the two natures. Okay. It is not the thing that it is only having a two nature, the every function having a two natures, but this is the problem. Any function, maybe more natures it will have, but any function, they are checking only that any function between these two possibilities. What are the possibilities? Any function, either it's a constant function or it's a balanced function. There may be more classification of the function, right? But the Deuce has worked on this, that he has taken the for the demo purpose, that can we have this problem, can we solve this problem, to check this problem fx, that fx is a constant function or a balanced function. Okay. So this constant and balance function, the students are not getting easily. What are the constant and balance functions? Okay. So for that, we can give a one example for this. So suppose there are 8 bowls and 8 dishes are there, and we have to check uh, that which dish is salty and which dish is sweet. Suppose 8 dishes are there, so we have to check the taste of the dishes, salty or sweet. So if we are going to check it, so there are possibilities in the dishes that all the dishes are having a same taste. So all the eight dishes are having a sweet taste, and or all the 8 dishes are having a salty taste. So if all the 8 having a sweet taste, it means that our function is constant. And if all of us salty, it also means our function is constant. Okay. So in this, when we convert into the 0 and 1 coding, we can say that if the function is all the values of the function fx for the different x, fx itself signifies but the students are not getting this. But fx is signifies that it has some value for every x. So x is the input and fx is the output. So x is the input, fx is the output, right? So mathematically, they are written like this: f function for 0, 1, and this one. They are written like this. So, yeah. Now, for the balanced means out of the four are sweetie and four are salty, right? So that means this function is balanced. So that means we have to check. This is a query problem in all the algorithm. The problem is of query problems. So this we have to check that function is a constant or balanced. Or in example, we have to check that this sweet example or salty. Now, what is the problem that we are proving the supremacy of the quantum over the classical? The main thing is that when we are going in the classical way, so in the classical way, what we have to do, we have to pick up a spoon for every 8 bowls, right? We have to pick up for the test. For every 8 balls, we have to pick up the spoon from here, 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 and here, like that, and we have to check, and then we have to tell. This is what the classical computer is doing. That he's picking the spoon from here, he's testing, he's telling is it sweet, is salty. So there are total 8 steps we have to follow. These 8 steps we have to follow, right? So minimum these eight steps we have to follow to prove that is it sweet or salty. So, and in the this is the worst case I'm talking about. In the best cases, so you may be knowing that complexities, right? Big omega n like that. So, in the best case, we can have n by two. N by two means 8 by 2 means 4 steps we can have. And we can test classical computer can give the solve the minimum 8 in the 4 steps. Maximum in the 8 steps in the worst scenario and best scenarios omega. But in the quantum, what we can do in the quantum, so we all things in a parallel. Why in the parallel? They are using the concept of parallelism. That means superposition. So Deuce was knowing that everything, every input, what the quantum will do, quantum will take a one spoon only. He will take from here, from here, from here, like that in a one step. All the things, some little bit. In all the 8 bowls, he will take a one spoon only, and he will take all the things in a one step, and will make a mixture of dishes in the one spoon. So that means this is called parallel loading. Parallel loadings, it will make a mixture. This mixture will be called as a superposition states. What the concept in the um, this quantum, right? So they will have a superposition state, and after that he will do some operation on it, on the superposition state. That operation is governed by Oracle. Then Oracle will do some operations, and after that operation, again we have to decode this superposition state. Again, we have to decode this superposition state. Now, how to decode this superposition state? Suppose I have taken this example. So let's take the decoding of this in this example itself. That suppose this these are the vegetables 1, 2, 3, 4, 5, 6, 7, 8. 8 are the vegetables that are here or dishes are here. Then what the person will do? There is a person is having testing the mixed state, right? Then what the person will do, depending upon their memory, it may be possible. We cannot mimic this example to the oracle, but yeah, I can give you some of the some of the funnier facts that maybe from his memory he will have a test of 1 and 2 only, or he can have a test of 1 and 3 only. He can have a test of 1 or 4 only, 2 and 3 only, like this. So if the person is sufficiently having all these tested in its mind, then he can guess the things. So this is the one way how the oracle can be performed. Okay. So oracle is a very hidden thing. We will discuss this in what inside the oracle is there. Okay. But suppose we have performed some oracle, and after the oracle, he will mark the things. After the oracle, he will give the solution, mark the things, and but that will also in the superposition state. That output will also be in superposition state. This is the input, but output should also be in superposition state. Now, from this superposition state, we have to we have to find out a final output. So now the thing is that this is only the pipeline I am telling. Now, what the real thing will happen? We will also come on that. But this superposition to the output, how we are getting this in? This I want to tell you by the interference, by decoding the interference pattern. So here they are doing inputs of parallel 8 dishes, right? Then all that input is causing a interference in it. Is causing a interference in it. All the waves has got mixed here, and they will cause the interference. Now, but this interference is something different. We will not concentrate on that interference pattern in the input, right? But it will go to the oracle. Oracle will perform some function. We are saying this function, but in reality, oracle will perform some mathematical functions, right? So we will perform some mathematical functions operation of that. This interference pattern will also come. There is a mixed state also. So from this mixed state, how to draw one output? This is the problem. And to draw this one output from this mixed state, what we are doing generally in the quantum, we are doing a interference. We are doing the interference, and knowingly we are doing the interference. For that, we have the operator. Knowingly, we are doing the interference in such a way it will give us a constructive and destructive things. So on the right answer, we have to do the constructive interference. And suppose this superposition is the mix of 8. And if we are measuring the first state, first bowl test, we want to measure the first bowl test. So we have to do the some operations in such a way that that operation we are calling interference. We have to do the interference in such a way that the first one output will be like this. and rest of the waves will be like this in this destructive. So the destructive will give you a zero result. The interference and this constructive will give you a maximum amplitude. So this is the real problem what we are getting in the output. What we can do, there is the output. What we are doing actually in the output, we will do everything by the mathematical function. No worry about that. We will do everything about the mathematical function. But this is the pipeline I am telling you. Then second step is to grow. Oracle will be also designed by us. Then after the Oracle, the resultant we will get in the superposition state itself. Then from that superposition states, again we have to perform some mathematical function. That mathematical function, what is the purpose of that mathematical function? To have the constructive interference on the right answer. Okay. And rest of the answer, we have to perform the destructive interference. So that means out of the 8 states, we want to measure the first state. So we will perform all the 7 states, we will perform the destructive interference. So we will do such type of mathematical operations like this. And we will perform the constructive interference through the mathematical operation so that the output of this one will be there in the final output result. Okay, so that is a pipeline, what we are telling it. Okay, so rest of the things you are, I think all of you are teaching there to the students that we are taking X gate, Y gate like that. Okay, but this pipeline, this is very important. So what exactly we are doing in the deuce? What we will do? We will have superposition states, and superposition states is only and only formed by superposition states is only and only formed by Hadamard gate in the classical. So this will be our starting point in all the three algorithm, that is Deuce, Grover's, and Shor's algorithm. All the three algorithm are pointing towards the 1 minute. Hmm. Okay. Now the voice is clear. So can I have some response in chat or in Sushmita ma'am? My voice is clear? Okay,
Yes, sir,
okay.
it is clear, sir.
Yeah, yeah, yeah. Actually, some of the queries I'm having, the voice was not clear. Okay, let's share the sharing the parameter again. So, so in the algorithm side, what we have to do on all the three algorithm, what we have to do, this is the very special property of the quantum that we can have all the inputs simultaneously inside the circuits. There will be a superposition of the inputs inside the circuit. That is very important property of the quantum. And this property is called quantum parallelism. And to impart all the inputs at a time, what we can do, we are doing a Hadamard gate, because Hadamard gate is the one that will giving us the this result, this result. That is the superposition states of all inputs. So if we will do the Hadamard gate at each inputs, then like this. Suppose this Hadamard gate we are applying for this input, another input we are applying Hadamard gate, another input we are applying Hadamard gate. Suppose there are 4 types of inputs I am taking for the sake of clearance, Hadamard gates. So they are applying parallelly. So that means what will be the output for that? The output for that is we are representing all these outputs like this. Suppose there are 4 Q2, Q3, like that, Q4, like that. The order of parallelism. The order of the parallelism is, suppose this is the 4 order. So we will write there are 4 gates, right? So the input 4 order means 4 inputs will be there. 1, 2, 3, 4 inputs will be there. We will write it here. And here we will represent that one by one gate, Hadamard gate. In this Hadamard gate, we will represent tensor product of 4 like this. So this is the representation of this small level parallel circuit of Hadamard gate. So from this circuit, what we will get? We will get the all the 4 inputs and combination of all that 4 inputs in input in the circuit. Input it in the circuit. So after that, we will represent the output for that. And what will be the output for that? Let me see here. What is the output for that? For that, output is represented by, it is given by this formula, 1 by root n sigma in input, whatever maybe we can take a constant x or something. Whatever the constant we will take, we will place the limit for that. That limit from 0 to, if we are taking 4, that means suppose in a generalized manner, if we will take n, the x is equal to 0, n minus 1. So if there is n inputs, then 2 to the power n. That will be the total number of inputs and stages, right? So 0 to n minus 1. Here, cat of input, whatever the input, suppose the input is x, this. So what it means, suppose we are we have seen this input in the Hadamard. Suppose Hadamard gate itself is the one order, right? So tensor product of one order, it will remain the same. And here 1 by root n. 1 by root n means 1 by, there are condition 0 and 1 only. So 1 by 2 summation. Now x is equal to 0 to and n minus 1. So 0 to 1, right? N is equal to 2 only. So 2 minus 1, that is 1. And here the x. So what we will do it here? 1 by root 2. First we will place 0. So cat 0. Then we will place 1. Cat 1. Like this. So, so in the input, we are getting the same. Sorry, output. This output we are getting the same. So that means now if we will include the order of 2, order of 3, we will increase that here 1 by root 4 like this, and the output will be 0 0 plus 0 1 plus 1 0 plus 1. All that states will be included here. That is 1 by 2 this cat 0 0 plus cat 0 1 plus cat 1 0 plus cat 1 1. So this will number of orders, and we will have this superposition state. So there will be the this will be the superposition states for n is equal to 2 like this. Okay, so we can go on like that. So this concept quantum parallel example, we have taken all the inputs parallel. perform the operations. The quantum computation is saying now you can perform the operations. All the inputs, suppose this is a solid input, this is a solid input, this is a solid input, this is a solid input like this. Okay, all that inputs yeah, 1 minute. Hmm. So I was telling the pipeline for that. The pipeline for that, suppose these are the four particles or five particles. And according to de Broglie, all the particles are in the wave shape also. So, so we cannot have this solid particles as it is here until unless we are having a de Broglie hypothesis. Okay. So time to time, point to point, I am inserting a physics set here, reconnecting the concept to the physics. That this is the very special property of the quantum. Okay, so I know the Deuce algorithm. You can have somewhere else also, no problem. You may be teaching in the last 2 or 3 years. Okay, but my thing is to add something which maybe you are not teaching. So there are very less probability that you are teaching this time. This connection is there. Okay, so that what I can add you, that is a special property of this FDP. Yeah, I'm reconnecting this physics concept so that particle are solid particles. We cannot have the all the inputs of the solid particle when the particle remains the solid or particle remains the particles. Okay. If we will have, then what we can do by having it will not have the unity. It is has a discrete nature like that. So we cannot say this is a superposition state. Okay. If we will put together all the five particles like this, how much closely you can put? Even then, you cannot say that this is a superposition state. No, this is not the superposition state. Okay. So the concept, the beauty lies at here. What the de Broglie said. That's why the de Broglie is very much important at here. What de Broglie is saying? De Broglie was saying that if these particles are wavy nature, if these particles are wavy natures like that, then multiple waves we can have, and when we are having the multiple waves, we can have a resultant wave, maybe deformed shape or maybe like this, maybe deformed shape, but we can have like this. This deformed shape we are having, right? So maybe the shape may be deformed, maybe the nature may be deformed, but it is having a single wave. Finally, we are having a single wave. So that this superposition is, we can call it as a superposition. Why? Because we are not seeing the existence of this particle at here or this particle. We cannot say which particle is present at what time. We cannot say. So this is the beauty for the quantum. That's why we are rerouting ourselves in the physics. Some uh, concepts which are always remains in physics. Yeah. So now coming to the this problem, Deuce problem. Yes. So we are importing pipeline. I was talking about pipeline. So what is the pipeline? So like that, because we are able to suppose this any particle or anything information to the wavy nature, so that we can have a superposition state. So like that, this is the beauty, and this beauty will reflect in all the three algorithms. So all the problems, why the problem is being solved in the quantum, why the quantum is said to be a supremacy in the as compared to the classical, because rather than having a one by one inputs loading, that is called a series loading, okay, we can have a parallel loading of all the inputs. And when we can have the parallel loadings of all the inputs, that means every field we can accelerate, whether it is a biological field or your IT field or some mechanical field, whatever field, electronic field, so chemical field, chemistry field, all the fields having us multiple inputs, and if we can parallel load that multiple inputs, then we can speed up by a many fold, right? Many fold means not one fold, two fold, three fold, or 10-fold. We can speed up by 1,000 folds, means 1,000 times or 2,000 times, like that, because it depends how many times, it depends on the inputs, like this. So that is the beauty lies at here. Now the main problem will remain. What problem? Yeah, superposition state that we can form at here. This is the beauty. So we can form. Now anything, any strength can argue, yes, we have formed the superposition state, but now what will happen? Okay, this is not the ultimate solution. Suppose we are having a wave like this. We are having a output wave like this. This is a wave of different defaulted wave shape. Okay. Now we are getting this output. Okay. Now how to retrieve the information from them? This is the main problem. So this pipeline, I'm telling the things behind the curtain. So how to extract the information from that superposition wave? Okay, we have formed this wave. There is no problem. We are forming. Okay, we mix this thing, but now the problem is when we are going to extract the information from the superposition state. So this extraction demands interference. This extraction demands interference, and in the interference we are only doing two things. So we have the two options only, constructive and destructive. When we have the two options, that means we can say, we can use it in this way, as I have stated earlier. That's that the constructive interference, for the right answer, for the right one, we can have a constructive interference. We can design our oracle in such a way it can have the constructive interference. Rest of the things we can have like this condition, cancel out condition. Rest of the things we will reduce to zero. That means in the output, automatically this option will be there. And because of this reason, why I'm telling this, not only the purpose of rerouting to the curtain behind things, the main purpose to tell this is that why we are only restricted to the query problems. So in all the algorithm, you know that in classical algorithm, all the algorithm are query problems, right? So the interference are having a constructive and destructive interference. It can only solve these two things. Either it can raise the amplitude of the right one and destroy the amplitudes of the wrong ones. Only it can do these things. So that means it algorithm, what are the how many query problems are there, we can solve very easily. Okay. So it will not give you a solution. Remember, keep in mind, it will not give you a solution. Yesterday, I also talking about that. It will not give you a solution. Solution that will be provided by the formula itself in the classical algorithm also. So we are giving the pathway only. So the pathway, how to cut the pathway, the length of the pathway by this beauty. This is the beauty, the parallel inputs. Okay. So this is the pipeline for that. Now, yeah, now coming to the main problem. So all that things is over. So the main problem is that Deuce was one wants to check this function is a constant or not. So to check this, he can use the Hadamard gate and parallelism concept at here. Everywhere he will put Hadamard gate. Hadamard gate, what it will do? It will form a superposition state, and from this superposition state, a oracle we will apply. So all the play from the oracle we will apply, okay? And after that, after this oracle, we will again, we have to do the superposition decoding, superposition to the input output state. That will, again we will apply the Hadamard gate at here. This is also the beauty. The Hadamard gate work at here like reversible. Reversible means we know in Hadamard gate we are applying 0. It will give us superposition state 0 plus 1 by root 2. This state we are calling positive state. Everybody knows this, right? This state we are calling a positive. Okay. If not knowing, then you can form it like this. So 0 plus 1. This is state by root 2. This is state we are calling collectively. We are calling a positive state. And we know that 1 it is giving 0 minus 1 by root 2. This state collectively called negative state. Okay. So at here, the Hadamard work is to convert this input to the superposition state. But at here, in this stage, the Hadamard work is to reverse. That when convert this into single output stage, like that. This is a superposition state. So convert this into the collapsing state, one state. So that's why we have to apply the Hadamard gate at the output also. Okay, so that will be the circuit for that. This is the in this circuit, this oracle is hidden. So what will be the oracle for that? The oracle circuit for that is C naught gate. This is the oracle combined with the Hadamard gate. This will be the oracle for the Deuce algorithm. So what are the inputs we will get it? We will get in the superposition state. We will have some mathematical formula for that superposition state. Then all that formulas in the form of cat 0, cat 1, 1, 0 like that. And all that mathematical waveform we will pass through the oracle. The oracle is a C naught. Then C naught will apply on that formula and we will get the output. From that output, we will apply the Hadamard gate. That is the circuit for this uh, Deuce algorithm. So, so this algorithm uses the superposition plus interference at the output, okay, and demonstrate parallel evaluation. So what it has proved? It has proved that the parallelly we can have something. The something is inputs. So parallelly we can have something, and by this parallel addition or parallel inputting of the parallel concept, we can get a output, which is the final solution for that. Either this is the function is constant or not. So this deuce will give us. So I'm not going the mathematical detail because we know that mathematics you can follow from the books. Okay. So that mathematics is like that. This fx we have to perform 0 and 1 like this. These are the mathematics. Then we will perform for the C naught gate, that is oracle. Then it will divide into the two cases. The either the f0 is equal to f1 is equal to 1, f1 is equal to f0 is equal to 0. This is the constant. We have to put these values to that. Then we will follow the results. Okay. So we are moving towards the net. Yeah, Oracle. I can tell you something about Oracle. So what is Oracle? Oracle is a very interesting story I want to share with you. Actually, all the things is not required. You will maybe some of the peoples will be thinking like that what to do with all these things, routing and all these problems, the routing in physics, routing in mathematics. Okay, that nowadays the era is teaching of era is like that. We have to we have to provide the cut to cut knowledge only, not in so much depth, in so much detail. Yeah, right, exactly right. I agree with whoever is whoever person is thinking about like this. Yeah, I agree with this point. But the main problem is that okay, you know you don't want to provide all these things to the student. In that stage, BTech first year, second year, third year stages, they are not able to handle all these things. But as a mentor, as a things, as an expert, you should know the routines. You should know the uh, uh, curtain behind things, right? So that is the main motto for this. Okay. So it is not necessary to provide these knowledges, compulsory this knowledge to the students, but as a mentor, you should have all these things in you. So whenever the situation will come, whenever the some more interesting candidate will come to you, as a guide, you will treat them. Then you can tell them all the things. So that is the motto. So whoever is thinking that what we can do by routing on all these things, we want only the coding, we want only how to run the codes, how to run the circuits. Okay, okay, I agree. Uh, but so the motto of the FDP is to go the things where we are not going normally in our teaching. That is the motto of the FDP. Otherwise, this will be a normal class only. So we are moving towards the yeah. I was talking about the Oracle. So Oracle. There is a very interesting story about the Oracle. So the story is that there is a Oracle of Delphi. You can search on the net also. There is a Oracle of Delphi in the Europe, right? So that is work as a uh, very the European peoples are having a very much belief on that Oracle. What the work of the Oracle is to tackle your questions, whatever your daily life questions is there. You can ask to that Oracle. That is the type of temple is there. As our India temples are there, or churches are there. So like that, that is the mythological temple is there in the Europe, Oracle of Delphi. So the peoples are used to go there. Peoples are used to go there, and they are asking their daily life questions. So we can live at this city or not, we can have this business or not, like this. So what Oracle is doing, Oracle having some mythological belief. What the Oracle is doing, there is a one person like a pujari type, the devotee they are having. So they are asking the question and they are telling the answer, and answers in the terms of some lines which you have to understand. That's it. So this is the function of Oracle. The European peoples were used to call it Oracle. So the Oracle is just like a black box. So how they are solving the query, how they are giving the answers for that, nobody knows. Okay. So you have to only ask the question, they will give your answer. So that is the work of the Oracle at that. And from that European concept, that Oracle is following everywhere, or in the mathematics or in the IT fields. So this Oracle is I follow also there in Ramayana. There is a Ram Shalaka Prishnavali. Most of the person may be knowing in the Ramayana. There is a Ram Shalaka Prishnavali. You can ask anything. You can ask anything to the Ram Shalaka Prishnavali. You can have a finger and go to the ninth finger. Go to the ninth. It will complete your chopai, and that will give you your answer in yes or no. You can search on the Google. So these things like work as a oracle. Nobody knows how they are answering. But this is a black box. Nobody knows how they are answering. This is like a black box. But yeah, it's answering like a yes or no. So this concept of oracle has been originated from that. So the Oracle of Delphi. There is a place still there in the Europe. So like that, there will be an oracle in our problems in all the three algorithms. There will be oracle. We have to design that oracle. So the matter is that every student is confusing at this point. That when we are
Excuse
teaching
me,
oracle,
sir. I'm sorry for
hello.
the interrupt.
Hmm.
Actually, can you please zoom your screen, sir? Faculties are texting like they are not able to see your screen. Can you please
Oh,
zoom it
okay,
little?
okay, 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 okay. They are able to see. They are able to see what I'm sketching here. I'm writing from the
Yeah,
pen.
yeah, it is fine, sir. No issues. But from one ma'am, just
Okay,
she just told to zoom the screen. Now it is fine, I guess.
okay, okay. Fine, fine, fine. Yes, we were at the Oracle of Delphi. So Oracle of Delphi is like a black box. So like that, all the students are confusing. So as all the interns coming to me, we are saying them to design the Oracle. They are confused. Why we are designing the Oracle and the algorithm? We are saying this. They have to find the answer. So Oracle is just like a black box, but the black box is for the unknown users. Black box is not for the designer. When you are the designer, you have the designer of the circuit, you will know this. Yes, 100%. Okay, it is not work as a black box for you because you are the designer. You have to design the circuit. Okay, so once you will design the circuit, then let the other be used here. Okay, let the other we use this circuit. So when the other will use this circuit, nobody nobody will see what is inside the circuit or inside the black box. They will see as a black box this circuit. Okay, so this black box world is used for the users, not for the designers. Always remember. Okay, so the students are mostly confused at this point. Okay, so that how Oracle will know this. So when anything is not knowing in the Oracle, Oracle is just like a black box. So what are the functions there? How to impart that function? So these are the things we know. Designer know the Oracle. Who is designing the algorithm? Who is designing the things? They know the Oracle, but the customers they don't know the Oracle. Okay. So the another example I want to give you. Suppose there is a mall. Suppose there is a mall. Mall are having a 15 floors mall. Okay. In the 15 floor mall, suppose on the sixth floor, there is a Reliance showroom. Okay. In the sixth floor, there is a Reliance showroom at the left side. Suppose. Okay. So, uh, what happens? The designer, the architect, they know. Reliance companies, they know. Okay. The owner of the mall, they know where it is. The Reliance mall, the Reliance shop. It is at the sixth floor because they have given the permission. Reliance management, they knows they are coming daily. Yes, they know. So this is at the left side, sixth floor. Go to the sixth floor and the left side. Okay. So this is not the query. The query is like that when the customers are coming, when unknown users are coming here, when the customers are coming here. So then when you have the designer for the algorithm and you have designed the pathway for the customer, that the Reliance showroom, you have decided this button for the Reliance showroom, and when they will press it, it will go to the sixth floor. So you are designing the algorithm for there. So customers are not knowing na. So the customers are not knowing where the Reliance showroom is there. For that customer, you have to provide the algorithm, you have to provide the pathway. So always remember that these Oracle designing, you are designing for the customer. So for the customer, this terminology is being used. That is black box, not for the designer. Okay. So this is the punchline in the algorithm. So this Oracle function works like a black box, but to the customers, not to the designer. Okay. So yeah, that is like this. So now there is a phase kickback. There is a one concept remaining, that is phase kickback. So I am giving this in 5 minutes. Then we will start some basic level Qiskit codings today. So phase kickback. Phase kickback is the concept that itself it is having the word kickback. So kickback means suppose in the C naught gate, actually it is working with the C naught gate only. Suppose in the C naught gate, this is the X. In the C naught gate, there is a control, there is a target. So we are having the truth table of the C naught gate like this: 0, 0, 0, 1, 1, 0, 1, 1. This is the truth table. In the input, this is control, this is target. So output, we have to see the control. Whenever the control is 0, output will not change. That means 0, 0, 0, 1. But whenever there is a 1, control is 1, the next bit will flip. That is 1, you will write control, but next will flip 0 to 1 and from 1 to 0. This is the output. This is the output for that. Now, now just see, there is a very much similarity that in a first sight you can know what is the output. Okay, what you are seeing the control. If the control is one, then you are changing the output. This is the change output. If the control is one, then you are changing the output. If the control is zero, then you are changing nothing, like this. So here, the value of the control is controlling the target. Okay. But in the phase kickback, kickback means it should be in the opposite. Kickback word itself telling that it should be in the opposite. So what is the opposite? Control is controlling the target. Okay. So here control coming as it is. This is the normal operation. Control coming as it is. The target is changing, flipping either 0 or 1. Target is flipping. Okay. But now instead of control, instead of control, if this condition will occur anyhow, that target will remain as it is. Target will remain as it is. Control, the value of control is getting changed here, either 0 or 1. Okay. The target will remain as it is. The value of control will change. And this value of control depends on the target. This is completely opposite condition. If anyhow this work can work, this gate can work, then this working will be called as a phase kickback working. Okay. If anyhow this thing will work, it is called as a phase kickback working. So what again I'm telling you, it's hard to understand in the first sight that control coming as it is control, but the target is flipping either to 0 or 1 depending upon the inputs, right? And this flipping is also dependent on the control. So this control is controlling this flipping. Okay. If anyhow the circuit will be like that, that instead of control, target is controlling the what will come to the output, either 0 or 1. Okay. So the control will flip either 0 and 1. So what will come in the output? So the target will decide and the target will remain same. The same condition. Control will remain same. Here the target will remain same. If anyhow, if this same gate will work like this, then we will call it as a phase kickback. Okay. And why the phase is there? Phase is there because, and that we'll understand later. The phase is there because we are going to change the phase of the control here. Okay. So, so the same thing, just opposite order. It doesn't mean that we will oppose this. We will invert this. We invert this to table. No, it doesn't mean. Okay. But anyhow, so we will see what is the answer for that anyhow. Okay. So that is one yeah, that is possible when the gate will remain same. The gate will remain same, but there is a coincidence that it is possible when there is a negative applied at the target. So there is a some type of magic is there. So there is a coincidence whenever we are applying a negative is there in the target. Whenever we are applying negative in the target, okay. Whenever we are applying negative in the target, we are getting this phase kickback action. Always remember. Whenever there is a negative applied in the target, we are getting a phase kickback action. In the phase kickback, whatever with the output, whatever in the control, it will have changed now. Now what change? So that change is formula for that is -1 to the power input. Suppose input x is there. So the -1 to power x x at here, then this is control, input is x, get x. Then in the output, we are having -1 की power x. -1 की and same input is there, cat x. Okay. So that means whenever the negative is negative means cat negative. Cat negative means Hadamard gate output, that is 0 minus 1 by 2 root 2. This negative, this cat negative. Whenever the cat negative is at the target side, this thing is happening. This thing is happening. So they are changing the phase. Why we are saying that this changes the phase? This, and why we are adding this factor. This factor is called the phase factor. Phase factor. As we know that in there we are dealing with the 0 and 1, so the value of x may be 0 or 1. So if it is 0, minus 1 to power 0, that will give you 1. Okay, because anything power 0 is 1, and minus 1 ki power 1, it will add a minus factor. Okay, so there are some situations depending upon the value of x input. Okay, so there are some situations, combination of situations like that, it will have a negative phase. Okay, and then most definitely the negative phase will have a negative when we are having the value of x is equal to 1. So when we are having a 1 and combination of negative at here, we will have the negative phase here. Okay, so this is called phase kickback. So it has the direct usefulness in the this algorithm, all the three algorithms. Okay. So, so rest of the algorithm we will cover after seeing some. So we are moving towards some Qiskit application. Okay. So rest of the two algorithm we will see after some coding of basic gates. So now I'm starting to have this Qiskit introduction. So please give 1 minute for that. Hmm. 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 So yeah. So the screen is visible to everyone. Hmm. So before starting this Qiskit lab demos, I just want to share something to you that in this, 1 minute, where it is gone. Yeah. So in this, the I will talk about something about some programming. How we want to do the programming at here. Okay. So first I will talk about classical, as I have taken from the classical to quantum transition in the course itself. So I just want to quote these classical things. Then we will take a transition from the classical to quantum coding. So what happens in the classical circuits? In the classical, we are having a bit 0 and 1. We are having the gate, AND gate, OR gate, and NOT gates. Then we are arranging all these things and we are forming a circuit in the classical, right? So these are the what the classical. The same thing we will do at here also quantum. Okay. So we are having a bits. Instead of bits, we are having a qubit at here. Instead of gate, quantum classical gates and or not gates, we are having a quantum gates at here. X, Y, Z, Hadamard like that. And then we will have a quantum circuits for that combination of that gates. How to solve the circuits? Mathematically, we know now from series right to left and this scalar multiplication and top to bottom and tensor multiplication we can solve mathematically. Okay, so same mathematical formula we will involve here in the quantum solution, right? The thing is that what we are doing in the classical, we are arranging the circuit and then we are giving the instructions to run that circuits in the classical languages. That instructions is passed from the classical languages. So what the classical languages are doing, that classical languages, C, C++, Python, Java, all that are the classical languages. So what the classical languages are doing, we are providing a part for them and we are giving the instructions for them. Suppose we are giving instruction print. So that means that print instruction is decoded by the machinery language or assembly language, and that in the machine and assembly language we are feed it that it is feeded that you have to perform this 0 1 1 0, this AND operation or operation or whatever. Okay, so this AND or all that operations again, that is executed by Boolean algebra, that is governed by the Boolean algebra rule. So we are inputting the Boolean algebra rules in the circuits in the machinery language also. So that machinery language converting that rules, this instructions into that rules, and that rules are running the circuits. And when the circuit runs, we are following the results. We are getting the result in the output. So the pipeline for that is hardware, gate. Okay, 1 minute. Hmm. Hmm. So what is the pipeline? Pipeline is that we are having a this logics means hardware. We are having a hardware. From that hardware, we are having a circuit. Then from that circuit, we are having a coding. We are having a coding. That is a pipeline for that. So same here we will follow. We are having a hardware. We will have the hardware. Then we will follow the circuit. Then we will follow the coding. In the classical, we are having a C, C++ for the coding, Java and all that. Okay, Oracle and all that. That are the software languages that are coding. That coding give you the instructions to the circuit that run this in this way and this way and this way like that. And these circuits are running through the hardware. Like that, same thing will follow in the quantum also. So we have to code. Now the thing is that in the quantum there is no software has been developed to code it actually. Okay, only there is a environment that is provided by the IBM and some Google. The Google Sirac is named there, and few of the these are the major level things, and few of the environment from the uh, minor startups which are running to make the quantum computation. Okay, so that environment is provided by IBM and Googles. Okay, so but that hard though sorry that's environment is basically supports the Python, basically from the Python. Okay, that we are calling it as a Qiskit. So Qiskit is basically supporting the Python. Okay, in the Google they are supporting the Sirac, but that is using the Python libraries also. Okay, so they have what the library is there. There are different libraries in Python also. What are the libraries are there? What are for that? Libraries are for that executing the commands. So all the vector components we are talking yesterday, all the vector components in that library, Anaconda and all that. Okay. So Panda and all the Python libraries are having all the vector elements are there. We can pick up the vector elements from there and we will run the circuits. We will run the things. Okay, codings. But that is for the classical. But for the quantum we need some additional things, and for that additional things to perform the circuit and simulation and all that, that IBM has provided, has made the library. That library is called environment, that is a Qiskit, and we have that Qiskit is basically run on the Python. So only what we have to do, we have to do some terminologies. We have to learn some terminology, that what world we can recall Hadamard gate, what world we can recall the some wire, what world we can recall the qubit, so that only that we have to learn it. Okay, and then the same thing we can run it in the Python. Same coding we can do in the Python. So I'm just giving some of the demos. So some of those demos for the basic circuit, how we can run it. So the all the information, all the vector components, so vector space. So this is called vector space. All the vector components are included in the Qiskit. This is provided by IBM basically. Okay, and that is supported on. They are running on the Python environment. Okay. So Python is a very broadly, you can say Hilbert space for all these things. Okay. So Python can be a Hilbert space for that, and Qiskit is the environment. Okay. So what we have to do, we have to first import these libraries. We have to import the Qiskit. We have to import the, and one thing, we have to import the simulator also. So in the classical, there is nothing called simulator, because in the classical we are having the computers ready. So directly it is going into the machine language. That machine language is converting into the that instructions, direct instructions. What ICs, what gate is running, and gate or what the combination of the gates are running, and what are the combination of the circuits, classical circuits are running, right? But at here, the no hardware, very rare hardware is present. So when rare hardware is present, it means we are having a hardware in terms of IBM having a 1000 qubit hardware, Google having a at least 400 qubits they have developed. The, but that qubits are taking a very much cost, that means to run, because it needs their all of the superconducting qubits. So tomorrow we will talk about this hardware side, what are the different type of qubits. But yeah, Google and IBM both are using superconducting qubits, and the superconducting qubits we need to run at minus 250 temperature, at least minus 200 to minus 250 temperature, that we need to run that computers. And so all that qubits, all that circuits is run by the qubits. Qubit is provided by the hardware. That hardware is running under the 200 minus 200 degree temperature. It requires a lot of cost. Okay, so we have to wait. We have to wait for the 2, 3, or 4 or 5 years until a ready-made solution for the commercial availability. Commercial availability means, so they are having a 2000 crores or 200 crores rupees of one computer, quantum computer. That is not the feasible, commercially feasible thing, product in the market. So until unless we are having the real hardwares ready on the market, so for but till then we cannot stop the development of the logics. We cannot stop the development of the software. Okay, so this will not be the case, or this should not be the case in the future, that maybe in the 1 or 2 years hardware is ready but the software is not ready, then we are starting the research on the software. Okay, it should not be the case, and that's why they have created the simulating environment. The IBM and Google and all that, they have created the simulation environment in the Python, in the Qiskit. They are giving that simulation environment to us. Okay, so that environment in the form of library, we have to import in the Python. Okay, so that is the very basic level knowledge I want to give you, that that all the environments first we have to import in the Python. Okay, and this is not easy. What I am facing issues in the 5 or 6 months. The Python are releasing their version. Okay, they are releasing version day by day, month by month, and it is very, very typical that to run some Qiskit codings in that same environment. So they are giving the some type of errors that this environment is not suitable for that. We are updating our command. We are updating like this environment. So PIC environment is converted to the IQ environment. MPL environment library is converted to the IQ libraries like that. Okay, so there are a lot of errors. So if after uh, going from this workshop, if you are not able to run something, then just check your versions, check your compatibility of the versions, and check the compatibility in going to the Python site, Python help. Okay, so what are the compatible there or not? So what I am facing from the last 6 months, there is a compatibility issues in the different versions of the Python. Actually, there are different versions of the Python. There are different versions of the simulator, and there are different versions of the libraries, right? So all has to be matched up to run the right coding. So if you are not having a right coding at your home or whatever, so need not to be worried. There may be a different issues of different versions. Okay. So we are starting the things. What we have to do? We have to import something at here. What we are importing at here? So very firstly, what we have to do? 1 minute. Yes. There is a set of instructions. One thing. Hmm. So first we will import the quantum circuit from the Qiskit. Then we want to copy all the commands at here. 1 minute. I will copy one minute. I will copy all the commands at here. Hmm. One minute. I am copying all the commands. Then we will show one by one. Hmm. Now I'm sharing. Yes. So what we are doing at here. First, I have imported all the commands at here. First, I have imported the quantum circuit command. This quantum circuits. Okay. Then from that quantum circuits, I have imported from Qiskit the visualization. I have imported the histogram, imported the simulator. This is the very important one. Here simulator. Okay. This is the command that if we are working on the hardware, then this command is not needed. So this is a simulator in this environment. This it will simulate and all the instructions will go to the simulator. That will simulate the circuit and will calculate it for us. Okay. So all that we have been given the commands to it, and so in the next, what we have done, we have given a one variable QC1, that is a qubit one, and we have imported the quantum circuit, that is one. In that quantum circuit, what we have to import, we have to import the Hadamard gate. So that Hadamard gate we are importing by this command, this. Okay. Then what instructions we are passing? The instruction we are passing to the QC1, we have to measure all things. And then either you can revert the things, draw, you can write first, or measure all, like that. Then MPL, this I was talking about, this MPL library, they are going to change in a 1 or 2 months. So the this warning is coming in my this Jupyter notebook. Okay. So the style, there are three common styles. Clifford, the two more styles are there. So you have to code, or you cannot write. No worry. Okay. So it depends. If you will not write this command, then also it will have something. So the circuit will be there. See, the circuit will be there, in fact, but what the warning will come? Warning will come that they are going to change it in IQB. Okay, so they are very shortly they are going to choose a new command. Okay, that's why we have done this. Okay, so from this command, so what is this QC1? QC1 we have said that this is the input circuit, and then the quantum circuit first, one number. Then we have imported this as Hadamard gate. Okay, and this zero by default. Okay, is in the zero state. Hadamard gate will remain in a zero state. Whenever you will import the Hadamard gate, it will go in a zero state. It will begin from the zero state. Yeah. Then do the command measure out. Then give the command drop. So you are able to have a circuit like this. Okay. So it will calculate how to verify this circuit. What are the calculations are there to verify the circuits? Actually, what here the Hadamard gate we used, right? So when we are using a Hadamard gate, the Hadamard gate, what they are doing, either they will work in a forward wise. Forward wise means taking an input, going to the output, or it may be the case it is working like a taking output, giving to the input, reverse wise, like this. So, so the Hadamard gate is converting one qubit to superposition state or converting superposition state to one qubit, right? So when they are doing like this, converting superposition state to one qubit, so there is a possibility in the superposition state, lot of states are there. In the superposition state, lot of states are there. So this is probability based. There is a probability and possibility what the state will come at the output. Okay, so always there is a because in the quantum there is a probability based condition. So probability distribution we have to obtain. Probability distribution means it cannot be. This is a very much drawback in the quantum also. It cannot be like that running in a circuit in a one shot, and we are very much sure as is the classical. Okay, so in the classical we are 100% sure the particle is present at the point A. We are 100% sure that particle is present at point A. But if we are saying this thing as a quantum mechanically, we can say 99% possibility is there and 1% possibility is there. It is not there, like that. So in a one shot, we cannot do just like in classical circuits we are doing. What we have to do to verify that, we have to run these circuits for the multiple times. That multiple times may be going for the 400 times or 500 times simulation. Okay. So the same thing we have done here. We have run job. We have run the circuit QC1. We have run the circuit QC1 and shorts. Shorts means 1024 times. That means this times is so much times, 1000 times we have run this circuit and we are following the results. So we are following these results and counts. So what are the results and counts that we are taking in the form of histogram? Okay. So now this is the histogram. So these are the commands we are doing, and here the histogram is coming. So see in the histogram, the 510 times in the histogram, 510 times. Okay. Some this output is coming, and yeah, 510 times this output is coming, and 514 times this output is coming. So there is a possibility. Okay. So and we have to check this possibility. Now going in a yes, there is a possibility that zero is coming in 510 times, and one is coming in 514 times. There is a possibility. So almost you can say that there is a 50-50% chances. Okay. And that is the output for the quantum gate. So there are 50-50% chances that zero will come and one will come. Okay. To verification of the circuit, this simulator works very well. Okay. We cannot go verifying in a real hardware because that takes so much consumption of energy and money. So in the simulation, we can verify our circuits, and this verification is must for all the quantum circuits, whether this is working fine or not. It's a very basic example. We need not to be verified because it's a Hadamard gate. It's a basic significant rule embedded at here. It will work like this. But if we are following a new circuit, suppose we are following the circuits like this, Hadamard gate, then X gate, then Y gate, then we are applying a Hadamard gate at here. So we are following a new circuit at here. Then it is necessary to run this and see the probability distribution curve. So what are the distribution of probability of output coming there? Okay. So that is necessary at here. So this, see here the count. So one count is coming 504, zero count is coming 510, right? So this is the basic circuits we are compiling here. So there is something, some problems is coming in the rest of the things. So I will rectify that. And tomorrow we will have some 1 hour demo for this Qiskit lab. Okay, and the rest of the things. So that's I'm compiling the session. Now I'm left in this time. 2 minutes. You can send your queries to the chat box. Hmm. So any query? Hmm. So what is on the y-axis? On the y-axis there is a count. On the y-axis there is a count. So we are representing the counts on that. Yeah. Any more query? So anything? Any suggestion? Any query? Anything? Somebody wants to ask something? Yes. The shorts associated with the counts. Yes. So that's why we are calling it the probability distribution curve. So probability distribution curve means if we are running, so suppose, so I can give you examples of because all of your teacher, we are running the experiment, basic physics, chemistry, all that experiments we are running in the lab, right? So we are running how much times we are running. If we are running a lot of times, we are getting the possibility of getting a right thing. So that's the errors get divided into that readings. So yeah, shorts associated with the count. If we are having a low shorts, then the count will, it depends on the probability distribution curve. Yeah, there is a definite relation for that. How to use these diagrams in the real time? Real time, whenever. Uh, so as we are giving these diagrams and our see here. Let me share one thing to answer this. So this is the very first circuit we are. This is the air simulator. Okay. So we are giving this output, oh sorry, this circuit to this simulator to run the calculations. So instead of simulator, we will give these circuits to the IBM, not IBM. You can give to the any of the quantum computer service provider. But nowadays, before 3 or 4 months, the IBM was having this service. They are providing the free account in the IBM. All of you can go and make the account in the IBM server, Qiskit server, and they are having a real hardware. So they are providing the real hardware simulation, not simulation, real hardware calculations for that calculations. So before 3 or 4 months, so the calculations are free for some more minutes, but now they have restricted only 10-minute calculation time for one account per month. Okay, and for the rest of over than 10 minutes, they are charging the money that is $1 or $1.2 per second. They are charging the money. So you can have a 4 or 5 accounts. So at least half an hour simulation you can do on the real hardware in the quantum in the IBM server. So same thing is happening in the Sirac. Sirac, I listened that, but I am not sure the Sirac is providing this type of service or not. But yeah, IBM is definitely providing this service to run these things in the real hardware, and they will give you the calculations. So this air simulation, this air simulation is the replication of that hardware in the software field. Okay, yeah. So anything else? Okay, then I think everything is completed. So okay, we will meet again tomorrow. So we are winding the session. Handing over to this Sushmita. Yeah.
Yeah, thank you, sir. Thank you so much for your informative session. We'll meet again by tomorrow at 3 p.m. Thank you, sir.
Okay, so thanks.
Okay, I think you all marked your attendance. So I'm just reminding, please mark your attendance without any fee. Okay, which is there in a chat. I've just shared it once again. So kindly mark your attendance. Okay, thank you all. I will wind up for the day. Thank you.